So you want to develop an embedded product that runs on battery. One of the problems that you're going to have is that these microcontrollers, even though they're very low power, by default, they're still pretty power hungry. And they will absolutely eat an 18650 battery for lunch. And in this video, we'll talk about some techniques that you can use to get many months, maybe even up to a year of battery life with your Raspberry Pi Pico powered project. I'm Josh, and this is Signal Drift. So you want to build a microcontroller project that runs on battery. You find the 18650 battery and you think, great, it goes from 4.2 volts down to, roughly 3.3 volts, maybe a little bit below 3.3 volts, and you can power your microcontroller using its onboard regulator. And it will handle up to 5.25 volts and all the way down to, I've tested this down to about 3 volts, which is right in the range of what these batteries will output. They'll output 4.2 volts down to around 3-ish volts. So how long is this project going to last on battery? The idea is that, maybe it will sleep for most of the time, right? Not do much of anything, and wake up periodically, take a measurement, maybe turn on Wi-Fi, send its measurement to a server, and then go back to sleep, right? That shouldn't take a lot of energy, and so it should last a long time on a single 18650 battery. These are pretty beefy. This one has a 3400 milliamp hour, assuming this isn't lying. That's actually pretty high for these. So a microcontroller should be able to, at least in theory, last quite a long time on one of these batteries. Let's give it a test, and we're just going to simulate running on a battery here. What we've got is we've got a Raspberry Pi Pico. This is just version 1.0. It's an RP2040. Nothing terribly fancy. I think it's bog standard. 2020. So this thing is now 5 years old. And we're going to see what it can do. So this is our first, what I call my naive attempt at saving power. So we've got our main loop here, we do some initialization, and then we say, while true, so we're going to loop infinitely. We're going to sleep for 60 seconds, and then perform some heavy calculation for about a second, and then go back to sleep. Let's go ahead and upload this to our microcontroller and run it from our bench power supply. And our bench power supply will tell us the amperage that it pulls while it's doing this. Great, so we've uploaded our naive code into the Raspberry Pi Pico, and now we're going to plug it into the bench power supply, and I've got it set to 3.7 volts, which is kind of a nominal voltage for an 18650. The voltage can vary widely, but it's kind of a middle voltage. So we're going to plug this in, and we're going to see what the Raspberry Pi Pico does. So we're pulling roughly 24 milliamps. Now that seems pretty low, right? I mean, that's not terribly high. So it's going to run for about a minute, and then we're going to see what the second of intense calculation is, the heavy compute. See how? So that was 28 milliamps as opposed to 24 milliamps. So my sleep isn't saving me all that much, right? The intense compute, you can argue about how intense it is. It was keeping the CPU busy, took 28 milliamps, and then when I'm just doing nothing, I'm taking 24 milliamps. Well, how bad is that? The average 18650 battery might have a 10 watt hour capacity. Some of them would be higher, but typical for a good battery would be a 10 watt hour capacity. So I need to convert my 24 milliamps into watts, and so to do that I multiply by the voltage, which is 3.7 volts, and that gives me the amount of watts that it's consuming. Then I can divide those 10 watt hours that the 18650 battery has by the watts that I'm consuming and get the number of hours that this battery will last, and that's 111 hours. I mean, that's not nothing, but that's 4 days. So this thing is going to run for 4 days on battery using this naive sleep. So we can see that the Raspberry Pi Pico, even when it's not doing anything, is actually consuming quite a lot of energy. But we've got some better methods of sleep. And so I have a second program here. So we're going to load the second program into the Raspberry Pi Pico. Let me walk you through this program. It's just going to first do basically nothing when it starts up for about 5 seconds. And then it's going to do a heavy compute for about 5 seconds. Then it's going to go to sleep. So we'll be able to see the relative energy consumption of each one of those cycles. And that deep sleep is a much deeper sleep. Here we take a look at our deep sleep function that goes into deep sleep until it's notified by the GPIO pin 1 going high. Here it calls some functions in the sleep library in the Pico extras library. What they do is first set up the clock to be running while it's in sleep, then it goes into sleep, and then there's a return function for what it needs to do when it comes out of sleep. And basically this just wraps the deeper internals of the Pico SDK with a nice user-friendly front end. This should be a real way to access much deeper sleep for the RP2040 and get much lower power consumption. Unfortunately here, I think that the currents are going to get low enough that the bench power supply just isn't that accurate. It's already not accurate in the 20 milliamp, 30 milliamp range. It's just not going to be great even lower than that. So if we're going to test this really deep sleep mode, let's give it a chance with a much more accurate device. For that, I have the Power Profiler Kit 2 from Nordic Semiconductor. They call it the PPK2, and it gives accurate readings all the way down into nanoamps. It will give you accurate readings of higher current flows and so forth, but it really specializes in very, very low sleep states and so forth, measuring in the microamp all the way down to the nanoamp range. So it's exactly what we need to be able to measure a deeper sleep mode. So to wire it up, what I'm going to do is I'm going to give it USB power. It's got these nice LEDs here that glow and pulse. It's lovely. I love this thing. We are going to turn the bench power supply off. So we could have the bench power supply be a pass-through. We're not going to do that. This can actually generate power. So it can be its own power supply and monitor the usage as you go along. So now I've got to plug the brown wire here into the output. So we're going to plug this in here. The software recognizes it, we connect to it, and we're going to say that we're going to do source metering, and we are going to output 3.7 volts here, right? So because we're trying to, roughly 3.7 volts, because we're trying to emulate an 18650 battery here. So we've loaded in our new program, and we're just going to do start on our monitoring, and you can see it's measuring the nanoamp range. So that's just noise, and then we're going to start our power output. So we can see 25 milliamps for the kind of quiescent phase, 28 milliamps for the heavy compute phase, and then we get down to 1.25 milliamps for the deep sleep phase. Now, this is great. This is actually getting into some serious territory here. So what's that mean in terms of how long it's going to last on battery? So my calculations tell me this will give us about 2,500 hours of sleep on a 10 watt hour 18650 battery. That's quite a lot better than we got with the just naive approach where we only got 4 or 5 days. So already we're doing a lot better. But can we do even better than this? You might think 1.2 milliamps is really super low. I mean, it's tiny. It's a milliamp. Like that's tiny. That's nothing. But, we're still only getting 105 days of sleep. 1.2 milliamps ain't nothing. And it turns out that most of that is coming from a regulator on this Raspberry Pi Pico board. A lot of that 1.2 milliamps is just the onboard voltage converter wasting power. As long as it's plugged into the battery, that converter is active and constantly draining energy. So what we're going to do is bypass the dev board's voltage converter and use our power profiler to get an accurate measure of the absolute lowest power levels this board can achieve. So to do that, what we need to do is wire this up a little bit differently. So we're going to come in here and we're going to disable the power output so we don't fry anything. And the fourth pin on this side is called 3v3 enable. And you might not know what that is, but if you tie it to ground, it will disable the 3.3 volt regulator on the Raspberry Pi dev board. But once you do that, VSys is now dead to you. You can't feed anything into VSys because VSys only provides voltage to the onboard voltage regulator. So what you have to do is you have to instead plug your input directly into the 3.3 volt backplane of the chip, which is normally an output, but now you're using it as an input. Never do this unless you tie the 3v3 enable low so that now you can inject power into the chip, and you have to provide 3.3 volts. So here, before we turn this back on, we're going to carefully go back down and adjust this to 3.3 volts. Stop it for a second, start it, and now let's go ahead and see what we can see. So we see the 21 milliamps of kind of the quiet phase. Now we see the 25 milliamps of the boost phase, and then we're down to about 600 or 700 microamps. So that's almost half of the consumption that we saw with the onboard voltage regulator. That onboard voltage converter is consuming roughly 500 to 600 microamps, just doing nothing. And that's months worth of battery. So we can almost double our battery from 100 days to 200 days on this, which is the better part of a year. If we want to add more batteries, so we could add more batteries, that will double it again. So now we're getting to the range where we can have a device that would actually last quite a long time in the field on a 18650 battery. Now, you might argue that I've cheated a little bit, right? Because I'm using this device here to provide exactly 3.3 volts to the 3.3 voltage plane, and we've bypassed the onboard regulator. The onboard regulator converts whatever wild and crazy voltages this thing produces down to exactly 3.3 volts. If we don't have that regulator, well, what do? Well, the answer is a low IQ buck converter. And TI has a number of these. Here's one of them. So this is a low quiescent current or low IQ buck converter, and it does 60 nanoamps quiescent current. So when it's quiet, when you have very low draw, that's its overhead, 60 nanoamps. And 60 nanoamps is so small, it might as well be zero relative to the 600 to 700 microamps the CPU here is consuming in its sleep state. Basically, this is for free. If you're creating a custom embedded circuit board, your design would have to include one of these low IQ buck converters, or you can get dev boards that have these low IQ buck converters on them, and probably also include like a battery charger for this as well. So anyway, I thought this was just a cool look. I'm working on a project right now where I don't have a device that's out in the field, but I have a device that I want to actually run off of a much smaller battery for quite some time. This is about a sixth the capacity of the 18650. So I wanted to run for a couple months without charging and wake up when I move it. So I've been researching how to get Raspberry Pi Picos to get into energy saving mode. This is an older RP2040, and its capabilities aren't quite as good as the RP2350 that I'm going to be using. It has much deeper sleep mode. So actually, I think I'm going to be able to get quite a lot of sleep time out of a very small battery using these methodologies. So thank you for watching. I'm Josh, and this is Signal Drift.